So early on you have charge accumulation in the well, and the central resonance is above the sea of the resonances of the Thomas Fermi, and then they drop down deeper, and also the electrostatic potential drops down deeper. So the emitter charge buildup in Hartree is smaller at high biases compared to the Thomas Fermi case. That results in lower potentials and into higher currents. So this was the chart I showed earlier, where I argued that this resonance is full at resonance condition of C1 coupling to E2 in the emitter. So the resonance is full. So that begs the question, what happens in the other bias direction? Right? What happens if you flip the device around or you apply the voltage from the other end? For graphical purposes, it's nicer to just flip the device around so I can compare on the same voltage scale and energy scales. So I'm going to do that. I'm just going to flip the device around and make this barrier on the left thicker than the barrier on the right. And now I can compare up and down like this. And I'm changing the condition effectively. Gamma left is no longer much larger than gamma right. It's in fact flipped. Okay, so if it's flipped, let's walk through that. If gamma left is much smaller than gamma right, and we substitute that in this equation for n, that means basically n is 0. Right? There's no charge in the emitter, in the collector. Not even neither emitter nor collector, no charge in the central well. That means just intuitively, well, you hop in at a certain rate, but as soon as you hopped in, you hopped out. Okay? And then you wait around for a while, statistically speaking, and an electron hops in, and it hops out immediately. There's no charge accumulation. In fact, there's charge depletion then. It's not quite charge depletion because the charge is still larger than the doping background. But it has dropped dramatically. If it dropped, the charge profile changed dramatically, the potential will change. We had argued before that if there's a lot of charge in here, it changes the lever arm of this RTD. So if the lever arm changes, your IV will change. Okay? So this case will not have any back action at all in terms of the central resonance being filled with charge. It will be virtually empty. That means our resonance, instead of being sort of floating up like a bobber on water, it should just pull down linearly. And indeed it does, right? This resonance doesn't float up in potential because it's virtually empty. An empty charge, zero charge in a Poisson equation means linear potential drops. Okay? That means the resonance basically goes down linearly. And indeed it does. That means the crossover from the central resonance with E2 and E1 happens at a much earlier voltage than in the case of the reverse bias. The lever arms have changed. Okay? So there's no evidence of this charge pushback. And in fact, you can argue that in this case, the Thomas Fermi and Hartree solution should be roughly the same. Because we know that the Thomas Fermi solution was underestimating charge in the well. Well, if there's no charge, there's not much to underestimate. So they should roughly be the same. So let's look at that. And indeed, the current voltage characteristic looks like this. Hartree and Thomas Fermi calculations roughly give you the same result. It happens early on in the curve when these peaks are aligned. And if you compare that to the previous case where we have the forward bias, you see that the peak is really indeed at an earlier voltage. And it happens also now that the peak current is much smaller. Okay? So the conduction band edges in forward and reverse bias look very different. So here I superimposed forward and reverse bias, and the colorful ones are the ones where the barrier is fat on the right, the fat in the collector. So the potential floats up. And in gray, I'm showing the fat barrier on the left, and basically the well empty, you see it a linear potential drop here, versus a little bit of bending in the other case. And basically the lever arm of the structure has changed. So you added a little bit of lever arm, in a sense, as the collector pulls down, you gave it a longer lever because there's no charge inside the RTD. That means it pulls it down easier. So the resonances move faster, so to speak. Okay? So finally, I want to look at charge occupation a little bit in the central device. We had argued that, so what I can do is, on the top curve here, I'm actually showing the current voltage characteristic in forward and reverse bias on a log scale. So that's why they look a little bit different, right? But basically you see a log type turn on, and then a turn off here, and a log type turn on in the reverse bias direction. I can compute in this RTD negative tool the charge density inside the RTD. So in the forward bias direction, I'm actually having a lot of charge. It's roughly 2 times 10 to the 11 at peak, and it turns on logarithmically, and then it empties out. Meanwhile, in the reverse bias direction, there is a little bit of charge accumulation, but not a whole lot, but it's basically empty. It stays roughly on the empty level. Okay? So the two forward and reverse bias directions indeed have very different charge profiles, which result in very different IV profiles. But remember this function I had written down here, this current is proportional to gamma right times n, right? So if that is really true, then the curve for the current and the curve for the charge should look the same by some scaling constant, right? I is equal n by some scaling constant. Well, it turns out that scaling constant is voltage dependent, right? We know our barrier on the right is energy dependent. That gamma is not an energy independent gamma. That means if you have toy models that assume some constant gamma that's energy dependent, like in many publications you see, note to self, be careful. Okay? It might work on a very narrow energy range. It does not work over a broad device that you apply a couple of volts to, or even in this case less than 1 volt. Okay? So it's really this I equals gamma n is not trivially valid, and it's an energy dependent function. So here are the key messages. An asymmetric RTD with different emitter and collector barriers shows dramatically different current voltage characteristics in forward and reverse bias. The different behavior in forward and reverse bias direction is due to charge accumulation and depletion in the RTD and in the two bias directions. Valley current is increased in the charge self-consistent calculation compared to the Thomas Fermi calculation in forward bias. And this hopping matrix element gamma is a strong function of energy. It's not a constant. Okay? So you need to be cautious about analytical formulas that assume that.